So yeah, I thanks for attending, you two. Maybe we'll get a few more. I apologize for the short notice. I ever since we had our review up at Weaver, um, I have been trying to figure out a time to do this. And with all the camps, you know how summer gets, the camps that my kids are attending and different things, it's just been a crazy ride since I left you guys. So um, in fact, tonight is working out because some other things got canceled. So I figured I'm just going to go for it, even though it's short notice. So sorry about that for anybody that was unable to attend, but thanks you guys for coming that are here. Um, so what I wanted to do with this, I want it to be valuable for you guys that are in attendance or anyone that might watch, but to get questions answered and things like that. So what I thought I might do, I want there to be a review. I don't want to do like a detailed lecture per se. Um, I have in the physics and instrumentation class that we did, I have 4 lectures that I did covering kind of all the equipment and the physics. And so what I was thinking is I've got those 4 slides pulled up. I want to review each one of them, but not in very much depth. So I want to go through in a fashion where I'm kind of just overviewing those slides and kind of reminding key points. And then as we're going along, if you guys have questions, you can just pop in and ask those questions along the way. And I'm going to try to like spend maybe 15 minutes on each of those 4 sections. So not anything massive. And then unless along the way, you 3 that are in attendance, if you have questions as we go, then we'll take the time we need to. But I figure if we spend about 15 minutes on each of those, that gets us through an hour. And then we can just kind of talk, about any other questions that you might have with physics and instrumentation and kind of where to go from there. Does that sound okay?
Sounds great.
Awesome. And I apologize. This wasn't official, so I wore my lax clothes for my day off. So you guys get to see me in the normal chill clothes. All right, so we got 5 here. That's good. We're moving on. Okay, so to get started, then let me move you guys over to my other screen. And see if we can get our slides pulled up. Sorry, I have these pulled up and then my computer made me log out because I had a glitch. So I had to reset and I thought they were back up. So let me hurry and log into my Google. Like we're getting a few more people here, so that's good. Okay, so I thought we would start off on section 1. Um, it's where we kind of go into the basic physics. So let me get my slide started and then I can share it with you guys. All of a sudden my screen is glitchy. Am I glitching to you guys? Can you hear me?
Yes.
Oh, good. Okay. Sorry, I'm trying to get this shared, but my computer is really struggling right now for some reason. Okay, can you see my slides? 4303 module section 1.
They're still loading on my end.
What was that?
They're still loading on my end, so I can't see them yet.
Sorry, I don't know why my computer seems super slow all of a sudden. You know,
Okay, I can see them now.
I bet you my son is gaming, so I'm gonna make him mad and get on my Wi-Fi and give my computer priority. Hang on just a second. Hopefully that helps. Okay. Okay, so section one, we'll get into the physics first. So to get started here, we'll skip some of these initial slides that are kind of GWAS slides. I do want you to remember, in terms of what we talk about most time, is gamma rays. Remember that those rays, they're a tight frequency, right? They happen often, so they're very strong, and they almost act like they have mass, but they don't. So we refer to them as a photon, right? We'll skip the difference between X-rays and gamma rays. You guys can look at that later. I think that's pretty understood at this point. I do want you to remember the energies associated with an atom. We need to remember what our protons do, what our neutrons do, electrons in the shell. The strong nuclear force is what holds that nucleus together. And then we have electromagnetic force, which is the difference between protons and electrons, and then the electrons themselves have some energy as well, right? So when we talk about some of the nuclear reactions, that's what the nuclear reactions are based on, is those initial energies. So just make sure you review those and kind of know what you're looking at. Again, this is one of my favorite charts because it shows how, what each thing does. Protons are physical characteristics, neutrons are nuclear stability. Remember how that proton-neutron ratio, and we'll talk about that. And then electrons are a chemical property. You need to remember that your atomic number, your Z number, is always going to be down to the left, and that's your proton number. And that's the one that we often look at to determine what an element is. Protons determine what the element is. And then your A number is the combination. And so most things that you see, whether on a test or anything else, will have at least those two. We talked about isotopes, isotones, and isobars, and isomers. So I'll let you kind of review that on your own, unless you have any big questions there. I do want to get to this chart. I think is important for you to remember and understand when it comes to physics. I pose a question, like, why is something radioactive in the first place? What's going on within the nucleus? And what's happening is it's up to that proton-neutron ratio, right? The nucleus wants to maintain stability, and what it's trying to do, remember, is that the protons have a positive charge and neutrons have a net zero charge. So the function of the neutron is to keep the protons separated enough that they can remain, that nuclear binding force can keep them together. If protons got too close, they would want to attract, push or repel from one another. And so the idea of the neutron is that it keeps it stable. And most things start out as kind of a 1-to-1 ratio, but as there become more and more protons, because of that positive charge they have, it takes more neutrons to keep an atom stable, okay? And so the center line that you see coming off here, that stability 1-to-1 ratio is somewhere around 38, and then it starts to get not so stable, and you get proton heavy. Right down the middle here, those are stable nuclides, and everything below is neutron rich, and everything above is proton rich. And so anything above that line of stability is going to have to be radioactive in some way, because the nucleus is trying to get back to that base state of where it's got that happy medium between protons and neutrons. Okay, so that's the whole idea of why is something radioactive. That's the reason. I have the chart of nuclides, and we'll kind of, in a couple slides, we'll go over this more, but we'll remember our parent-daughter relationships. When you look at a chart of nuclides like this, it identifies parent-daughter relationships, and you can also tell which way it decays. So you've got beta negative. It would mean that the parent, you would decay up and to the left. On a beta negative, if you're an alpha decay, it would be down to the left. And beta plus would be down and to the right. And so you can see some of that here. You can see molybdenum right here. That's your moly generator. And it decays by beta minus to tech 99, which is what we use, right? So you can see that relationship there. So you may want to briefly kind of review those relationships and what they mean. This chart, I would say, not as important to look at as understanding the modes of decay themselves, which is the next few slides. This is super important. I can easily see getting questions about, what is alpha decay? What is beta minus, beta plus? Understanding principally what they do. So these next few slides are definitely important ones that I would spend some time reviewing. Remember, alpha particles, sometimes called fission. I've seen test questions about fission. That's an alpha particle coming out, emits 2 neutrons, 2 protons. And so our atomic number, or our Z number, because 2 protons are leaving, it's reduced. And so we get a different element, right? Whenever we change the number of protons, we get a different element. The things to remember about alpha decay is that it's a very big particle, so it's super strong. But again, it can't travel very far. Simple piece of paper can stop an alpha particle. So can't travel far in tissue, but it is very, very damaging, okay? So again, the one example I have down here is Xofigo for metastatic bone treatment, which I don't even know if they're using it that much anymore, but it's a good example of an alpha particle. So they can send it in, attach it to the bone metastases. It doesn't travel very far, but it damages really bad, and so it can kill those bone metastases. So that's alpha decay. Remember, a full two of each is coming out. Beta minus, what you can remember about this, I always think of, when I think of beta and I think of the minus and positive, you're going to notice that if you think of minus, that's a negative sign. You're going to have neutron excess. And then you'll notice on beta plus, there's a plus sign and it's positive or proton excess. So that's kind of a way to keep it straight in your head on what you're looking at, what does what. But in beta minus, you have that neutron excess. And so because it has too many neutrons, what it will do is it will get rid of an electron from a proton, and then of course that becomes a neutron, right? Because it loses that positive charge and becomes a net zero charge. And so that's what you'll have on your, I mentioned when we did these lectures, I highly doubt your test talking about a neutrino, so don't worry about the anti-neutrino. I just want you to think of neutrons and protons. And again, in beta minus, remember that's negative, so you have too many neutrons, right? So we changed by transforming that proton into a neutron. Again, because something's changing with our protons, we're going up by 1, then that Z number changes. So again, we change to a different element. When you change to a different element, that's called transmutation. So any of these where it's changing from one nuclide, I shouldn't say element, I should say nuclide, one nuclide to another, that term sometimes may be used on a test called transmutation. So again, the example here that I used on the chart a minute ago is molybdenum to tech. This can travel about 1 centimeter in soft tissue. Again, that's something to know, right? That's easily a board's question, that how far it travels, what it's getting rid of, how it's working. A good example that's common, I-131, okay? We don't image beta minus. In I-131, there's a gamma that's given off as well, and that's what we image. But we, of course, do use beta decay when we do I-131 treatments, right? So then beta plus, sometimes called positron. Remember, there's a plus after, that means positive. So now I'm thinking I have too much positive, proton excess, right? Positive doesn't rhyme with it, but it starts with the same letter, positive and proton, too much protons, okay? So again, what happens here is that the proton is going to give off its positivity in the form of a positron, which you can think as a positive electron. So it gives off that positive electron. That positive electron travels a short distance, finds a free electron, which is negative charge. So you have same mass, and they have an annihilation reaction. Okay, when they have that annihilation reaction, 511 keV, or on this chart it says 0.511 MeV. That's just changing from kilo to mega, which would be 3 decimals. Don't worry too much about that. Just look for 511. But it would keV travel exactly in the opposite direction. Okay, so obviously this is what we image in PET. And I will say right here while we're on it, remember that we don't image positrons, right? It's not the positron we image. These are still gamma rays. They're just gamma rays that happen in that exact opposite direction, okay? So keep that in your mind when you think of beta plus. And when you're thinking of just questions that may be around PET application. Electron capture. I don't have a great super way to memorize electron capture other than if you think of the word itself, electron capture, why would you capture electrons? It's because you need some negative. If you need some negative, what does that mean? Well, it means you have too much positive, which is protons, right? So that is a way to just logically think. I'm capturing an electron. Electron's a negative charge. So obviously I have too many protons. So that's proton excess, okay? So this is where that K-shell electron is stolen down into a neutron to create another proton, or excuse me, I said that wrong. Stole down into the electron stole down into make a proton into a neutron, and that create that stability. Okay, so in this case, we end up with less protons than we started with because one proton turns into a neutron, so that Z number is going to go down by one. Okay, captured from the K shell. Anything that's done with electron capture is then going to give off some characteristic X-rays as well. So you may have some gamma rays from just excitation of this event occurring, but you'll definitely have characteristic X-rays after that K-shell refills and you have that shell reaction throughout the nuclide. Isomeric transition and internal conversion. The book, Waterstrom uses these terms. The term you use most often in practice and could even be on the test is gamma emission, but still remember to recognize that isomeric transition is gamma emission. These are the same thing. You could use those called the same thing. And then internal conversion is something that happens inside of isomeric transition. So that's the way to think of this. And I kind of have this all listed here. But just remember that our gamma rays, our gamma events, aren't a matter of the proton-neutron ratio necessarily changing. It's just that the nucleus of that nuclide is in an excited state, and in that excited state, it gives off excess energy. Often this happens because one of those other decay methods occurred, and once it did, then there's just was energy excess state that then kind of released, and that's what happens with gamma. Okay, and so that's what our Tech 99 is gamma, but that's also why in I-131, even though I-131 is a beta minus, it still gives off a gamma as part of that reaction, and that's why. So it has some isomeric transition as part of just giving off that energy state. Okay. Internal conversion is any time that gamma ray coming off the nucleus, sometimes it can be powerful enough that it will interact with maybe the K shell or another one of those electrons and kick that electron out of the atom. We call that an Auger electron. So if on the test they're like something about Auger electrons, you just need to think internal conversion is happening. Gamma rays have hit something off and it takes off. So you end up with characteristic X-rays. You also end up with that nuclide, that energy that came off. So say it was a tech, it came off as a 140 keV, right? It came off that nucleus, but it hit into the K shell, and that K shell has about a 21 keV binding energy. And so when that was released, that 21 stayed. And so you don't get a full 140 keV. Now, why is that important? Well, when we set the window limits on our camera and we're looking at our photo peak and we are saying we want you to find 140, if there's something coming off in the neighborhood of 120, we don't want it, right? And so it can cause some issues with our energy resolution in our camera. And internal conversion happens in a lot of gamma reactions. Most of them have some internal conversion, but we want to use things that have low internal conversion because they work better. We get the energy we want. So I listed down here that the internal conversion of tech, about 88% of the time it's a 140, 12% of the time we get that internal conversion. Okay, so these are probably really important ones to know and to review. Like they'll for sure be on your test. know how these forms of radioactive decay happen. That I would say that's one of your probably your most important things in the physics section is to really kind of have that down. So if you don't, these would be good ones to review. Also online, on Canvas, I have posted these slides already. So you should be able to get the slides that are on here today. I've also made my YouTube channel I have it private most of the time just for a link. It's open like public right now, so you guys just can go on there and look at videos of what we've done throughout the year. So if you want more than this basic review, you can go watch any of those lectures that you want. But definitely know those things. In terms of decay schemes, I don't know if you'll get a lot of decay schemes. You should know it. Just think of it this way: when you look at a decay scheme, the atomic number, which remember is your proton number, right? When we have decay, most of the time that proton number changes in some way, shape, or form, right? When we think of alpha, the betas, it's going to change in some way, shape, or form. So all a decay scheme is showing you is what kind of decays happen. You can look at it and know what happens. So in the case of an alpha particle, so when we lose protons, then it always decays to the left. When we gain protons, it decays to the right. When we do gamma emission, it decays straight down. So if you're looking at a decay scheme, just remember to the left, proton numbers changed. Why? I can go back and then think, okay, alpha, beta, which ones make less protons, which ones make more protons, and then gamma's coming straight down. So if you get anything that's a decay scheme, that's what you're looking at. That's how to kind of analyze that if you're looking at it. So that's a good one to probably review as well. And then this is just another. I liked both of these to look at in terms of learning, so they're both good ones to look at. You can see what happens. I like this one because it shows the Z number here, and then it shows like Z plus 1, right? And it becomes a different element. And you have X, Z minus 1, a different element. So that's how you read this chart. Another good one to review. We talked about metastable is just the idea that anything that pretty much most of what we use is considered metastable, but we often say TC99M, meaning metastable. All metastable means is that you have a half-life that's measurable and usable. You have some gamma reactions that when they happen, like say they're a part of beta minus or beta plus, they just instantaneously give off that energy and then it's gone. Whereas something like Tech 99 is going to give off that gamma ray for a 6-hour half-life. So it's a sustained period. So something that's not stable, when they say it's not stable, it means it's stable, it gets rid of it, and now it's not stable, it's radioactive, gets rid of the gamma, and then tries to become stable immediately. Whereas Tech is meta. They call it meta because it kind of stays in that same state for a certain amount of time. Okay. So if you get any questions on what does metastable mean, that's what they're after with that. There's I-131, and I put this one on before and I do now because again it shows the beta minus, but then it also shows the gamma that's coming off as part of that reaction, right? And this is what we image. I don't love that this chart has MEV. We usually think of things in KeV, but again, there's that 364 KeV is what I-131 has, right? There's another kind of chart, kind of like before. I'll skip that for now. Interactions with matter. Understand the photoelectric effect, coherent Compton. Some of that will be reviewed from if you've done like your X-ray stuff. But generally understand what a photoelectric effect is. That's a photoelectric effect. You have an incoming photon of whatever kind, right? This could be an X-ray and it could be a gamma ray. Any kind of incoming photon or energy that knocks a K shell out. K shell takes off. It emits characteristic radiation. And then the thing to remember here that becomes important in imaging when we talk about how our gamma camera works and so on and so forth is that the photoelectric effect, the incoming photon is totally absorbed. Now, when we talk about that in terms of equipment, that's good. That's what we want. We want to absorb because then we can measure. When we talk about the photoelectric effect to a patient, that's not necessarily good, right? And that's what you learned when you were in X-ray is like, we don't like the photoelectric effect because they're absorbing all of that dose. Okay, so that's something where your brain might be a little twisted, but just remember photoelectric effect is good for imaging a gamma camera. We have to stop something so we can measure it. we don't like photoelectric effect in terms of patient and their dose. Okay. And then coherent and relay. Coherent is where incoming photon comes in and it scatters, right? So this just, the only thing this does in terms of a patient, it increases dose. In terms of a camera, this could cause our energy resolution to not be great because we have other types of radiation going on that might be captured by the camera that aren't that 140 or that 364 for I-131 or whatever it is, right? So you don't want coherent scatters. Coherent scatter is not good, for a patient. It's also not good for imaging if it is able to get through to the camera. And then Compton scattering, kind of the same idea. You can get Compton scattering, and you'll see when we look at a photo peak on the next set of slides that Compton scattering often shows up, and that's just you get that naturally from the different components of your camera having photons strike and have some scattering that occurs. Okay, so I think that is it on this first set of slides. Does anybody have any questions on that one? That's kind of your basic physics of radioactive decay. Okay, I'm gonna take that as a no, or you're all muted. Just kidding. All right, so let me stop the share on that one. I'll put the next one up. So the next one is gonna be our gamma camera. That pulled up. Okay, you guys see that one?
Yes.
Thanks, Stephanie. All right, cool. Okay, so let's get into this one. Kind of skip some of this introductory stuff. You can look at a little bit what we cover in this slide. Let's see. I guess this one's not necessarily important, but just remember that all we're trying to do with anything that we measure with in nuclear medicine, whether it be a gamma camera or anything else that we use, we're pretty much just trying to see gamma events, where they happened in time, in space, when they happened, and their energy and concentration. If we know the energy and concentration and we know where they happened on the patient's body, that's the main thing that our gamma camera is trying to do, right? Is see when it happened, where it happened, and how strong it is. That's the ideas. And all of those three things play into what we mean when we talk about how do we get resolution, or how do we get sensitivity, or how do we get any of that kind of stuff. We just have to think of that. Like, you're trying to catch an event, where it happened, how strong it happened, and when it happened. Okay. Let's skip a little bit of this. So when we talk about our detectors and we start talking about those, we need to remember that there's kind of two main principles when it comes to detectors. It's efficiency and sensitivity. Okay. You might also call efficiency, well, I'll say this: efficiency and sensitivity are very, very similar things. We're also going to talk about resolution. Okay. And so, and we're going to talk about how those interact with each other. So this is how sensitive is a gamma camera. And there's geometric efficiency, intrinsic, and photo peak that all are kind of playing. And as we talk about the camera, that's really when you'll kind of see them more and be like, oh yeah, that's what we're talking about. So I'm going to skip over a little bit of this. This is like general explanations before we get to the meat. And so I'm going to skip this. I said a minute ago, remember the photoelectric effect. And let's get to, so system resolution is the other thing we'll talk about. We'll talk about energy resolution. We'll talk about temporal resolution and spatial resolution. When we talk about those three, that can get confusing because most of the time when you guys are used to hearing the word resolution, you're thinking about like the sharpness of an image, right? And so it can get confusing when we talk about something else. So when we talk about energy resolution, all we're saying is, can your gamma camera discriminate between the types of energies that the camera is seeing? So when we end up at the end of our camera and we get to the computer, we end up with what's called a photo peak, and we'll talk about that. That photo peak represents the energy that it sees. So on a tech, if we're imaging tech, that photo is going to peak at 140 keV, right? And if everything was perfect in your camera, all we would see is one line at 140. But when you look at a spectrometer on your camera, you see a wave, right? You see a pulse or a peak. And the reason that that has some width to it, and it's not just this skinny little 140 thing, is because there's lots of things in your camera that give you slight bits of different energy resolution, whether it's scatter, in all these events, anything from where a photon comes off a patient to where you get an image and it reads that pulse, there's an opportunity for it to not be perfect at 140. What we want is perfect, but there's opportunities for it to not. So when you say energy resolution, you're not talking about the sharpness of the picture. You're talking about your camera's ability to be able to correctly read and look at that energy and not have a really wide energy that it sees, but a more narrow energy that it sees, okay? And when we talk about full width half max, that's what we're measuring is energy resolution. Temporal resolution is just the idea of, can I convert a photon to an electronic impulse, and can I keep that the same along the whole time? And can I do that, and how does that work in each of my systems that I use? And then spatial resolution is more of what you're used to, the system's ability to demonstrate detail and sharpness of where an event took place. Okay, so that's the resolution. System resolution is spatial resolution is what you're used to on any other imaging that you've ever done, right? And the temporal resolution is energy conversion, and the energy resolution is ability to see what we want to see. Okay, so those are just 3 quick ways to think of that. And those get confusing, I know, because it uses the word resolution. Obviously, when we're thinking about gamma cameras and how they work, and you guys know this, I heard you all say it in review, but photons travel 360 degrees. So we have to think of that when we think of how gamma cameras and collimators work. So collimators, right? I love this one because it has a picture of what a collimator actually looks like. It's so much better to look at something like this than these little written out charts, right? These graphics make things hard to understand. Just remember, the collimator looks like this. So these are very small. These are a few millimeters wide. But what you want you to think of, if it says like, what does a collimator do? If you have a question that's like, what is the purpose of a collimator? These are your answers, right? It defines the field of view and reject unwanted photons. That's really what it does. This is the main thing in your camera that allows you to have sensitivity, or the gathering of gamma rays, and also be able to have some form of resolution. Without them, we could not have resolution. So remember, we got bored holes and we have septa. And depending on what we do with those, we change the difference between resolution and sensitivity. And we'll get to that on the next one. But here's another good idea of how a better way of how they work, right? So anything that gets between those septa at 90 degrees is recorded. This is where the spatial resolution happens in a gamma camera, right? Because if something goes straight up and it makes it through, it's going to happen on the image exactly where it happened on the body. If it's slightly angled, it's going to happen at a slightly different place. And that's why in nuclear medicine, we get about 3 millimeters worth of resolution is about what we can get on a plane image, and about 12 meters when we do a SPECT and we reconstruct, because we just don't have something that's represented perfectly. It's represented most of the time just tiny bit off of where it actually happened. But our septa would allow that to even happen at all. Otherwise, it would just be light, okay? So just remember that. So collimator sensitivity, if we were to define that, since we've kind of already mentioned it a few times, sensitivity is just think of it in the most simple way is the available gamma rays coming off. How many of those do you actually gather and use for an image, okay? The more photons that you gather, that means you have higher sensitivity. If you're able to gather more, it is more sensitive. And just think about when we talked about statistics, right? The more counts we have, we can show that our sensitivity and accuracy go up, right? We did that with the math. So whenever we have a more sensitive scan, more accurate scan. Okay, that's what that's thinking. And so the things that affect sensitivity is the borehole diameter, because if you have a bigger hole, more can get through. If you have a more narrow hole, less can get through. Also, the septal thickness. Let's say you have a hole, but you have either a thin septa or a thicker septa. That's going to take room in that space, so that septal thickness can affect it. And then borehole length. And the reason being is that if a borehole is really long, it's more likely to cut off a photon that's traveling just slightly off of 90 and let a perfect 90 only through. Okay. So when those boreholes get longer, our sensitivity goes down. Okay. When the borehole diameter is bigger, we're greater sensitivity. When septal thickness gets thicker, sensitivity goes down. Okay. And then resolution is the competing factor here when it comes to our collimators. Remember, resolution and sensitivity are inversely proportional. You can't have both. You have to give and take, right? So resolution comes from perpendicular photons. They're going to give the best resolution. When we're slightly off, it's a little less resolution, but if we get them perfect, that's the best case scenario. So the way borehole diameter affects this is that if you have a big wide borehole, then all kinds of angles can get through, so we have low sensitivity. But if our borehole is very, very narrow and tiny, then only 90 degrees can get through and not a lot of other angles will get blocked, right? So that increases our resolution. If borehole length is increased, then you're going to have more straight photons coming through and more likely one that's slightly at an angle because it has to travel such a far distance through that borehole is likely to get hit, right? So that borehole length. And then distance can affect that too, and I'll show you in a picture. It's better to understand that one. But remember, all of these are pretty much opposite when we do the sensitivity, right? How they work. Because anything you do to increase resolution usually cuts down the amount of photons that you get to see. And anything that increases the amount of photons you get to see, generally that's more angles through and your resolution goes down. Okay, so those are inversely proportional. Here's the graphic to show how length matters. So this is supposed to represent the radiation source in the exact same spot. When we have these short septa, then obviously it's the angle of that is able to come through. If we lengthen those septa straight out, you'll notice now that more of them are being blocked, right? So what does that mean? It means when my septa are longer, that my sensitivity goes down, but the resolution goes up because less angles. When my boreholes are shorter, then my sensitivity is increased because more get through, but it's not as good of a resolution. Okay, so there's your borehole length. This is all definitely, I would say, important ones. These are going to be questions. I can almost guarantee it. I could see this fact right here being a question as well. Less than 1.1% of gamma rays actually make it to the detector. So we're not actually that sensitive in the first place. But we have to be that way. Otherwise, if we accepted everything, we wouldn't have a picture, right? So I kind of listed those right there, the inverse relationship there. Distance. We talked about distance. This isn't borehole length, right? So this one was borehole length. That was just the borehole or the septa getting longer. This is that how does distance affect my images, right? And what you'll notice here is that when you bring the camera, your camera heads closer to the patient, what we're doing is we're upping our resolution by a lot, okay? And we're cutting out some of those photons that go in weird directions. Now, the thing that might not be inherent to you, if you look at this chart here, parallel collimators are what you're going to use, 90% of the time. And you'll notice that the sensitivity on that parallel collimator actually remains pretty close. Now, this is moving your patient, right, further or farther away, because you're still going to have straight photons and everything straight. So if you get them a distance far away, you might still be getting the number of photons, but if anything, your sensitivity, maybe goes up a tiny bit when you're farther away because more can get in, but it's not enough that it makes a difference. I think there might have been a question on that in one of those tests you guys did is that what does it do to sensitivity? It doesn't do anything, but you'll notice that every kind of collimator, when your patient is farther away from it, it reduces the resolution. So that's the reason why we keep patients close. So if you have a test question, make sure, what's the reason why we get the patient close? It's resolution. It ups resolution, ups resolution, ups resolution. Now, on these different types of collimators, you'll notice like converging collimator, it comes down a little. Converging, it actually increases sensitivity. Pinhole is way down, right? Because you're just getting through that tiny little millimeter aperture. And a thyroid probe, same thing. But the main thing I want you to think about here when you look at this and when you think of distance is it massively affects your resolution with your patient or with your images. Collimator classifications, you should definitely know this. What makes a collimator a different energy level? We talk about how we have general purpose collimators. We have low energy, medium energy, high energy collimators. The difference is that septal thickness. Okay, so high energy collimators would be made for something within the 300 to 400 keV range. Medium energy 200 to 300 keV, and then low energy like 60 to 140. That's our tech. You can get a little higher than that, but that's kind of what the book lists. But remember those ranges. So understand the only thing that really makes them different is that they're going to make this the septa are thicker, and right. The reason the septa have to be thicker is because if you have a higher energy, you've got the septa are designed to stop those angled photons, and so you've got to be able to stop them, right? So that's what makes the type of energy of your collimator different. Also, remember that there's different types of collimators that you could be tested on. Understand what these collimators do to your images and what they might do to resolution and things like that. So I have all these listed on the slide, but when you have a diverging collimator, a couple of key things to remember is that you can take a really big object, an object that's bigger than your detector, and because your septa angled out, it can see that bigger image or that bigger patient, and it's going to project it in a minified way on your detector. So minified, okay? It's going to reduce the sensitivity a little bit. Why? Because X-rays are traveling out this way at 360, and your detectors are exactly opposite. They're angled this way. X-rays are angled, or excuse me, gamma rays are angled this way, right? So you're going to have some reduced sensitivity. Remember, you get a minified view, but the positive is that we can get a big object if we have a small detector, okay? Converging is pretty much exactly the opposite. What you're going to end up here is it's going to take a smaller object and it's going to magnify it a little bit. You'll notice this increases sensitivity. Why? Because the 360-degree pattern that the gammas travel, that collimator matches that 360. So they're very it does increase that sensitivity. Okay, and again blows up an object. So magnify, increase sensitivity. Then your pinhole is designed for very very small imaging of organs, right? A lot of departments will use this on thyroids. There's some departments that use it on like bones in the wrist, like navicular. This is going to be a very magnified view, and it's a very, very good resolution. And that might not make sense to you looking at this because there are only two septa. What you have to remember is that it's kind of like having one borehole that's very small, like 3 millimeters. And so because it's only 3 millimeters, it doesn't let a lot through, but they're not straight. So it lets everything through in a spectrum, and it works a lot like an eyeglass. So everything on the left of the image is going to be projected to the right. Everything on the right of the image will be projected to the left. So it flips your image and it magnifies it by quite a bit. So really good for detail. So remember, magnified, really good resolution, good for detail. You might imagine though sensitivity is pretty low here, right? Because we're just working through a 3 millimeter hole. So any questions on collimators before I go on? I'll kind of ask. It's a good spot to ask that. Okay. So now we're going to start to think about the energy transfer from a photon to a signal that is electronic, right? So scintillation. Scintillation is our first thing. The whole point of scintillation is that it's a crystal that will give off light when struck by a photon. So the crystals that are used in your gamma camera are sodium iodide. They're thallium activated. Let's talk about that because I know they'll have that principle there. In fact, we'll talk about it in a couple slides, but as a simple version to say right now, just remember that it's a sodium iodide crystal with a little bit of thallium, or what they call thallium doped or thallium activated. It has a little bit of thallium, and what that thallium essentially does is it makes it so that when the light is given off by the crystal from the gamma ray reaction and the excitation that happens in the crystal, it makes it so that it gives off energy in the visible light range rather than a range that is outside of our visible range. If you did not have thallium in a sodium iodide crystal, it would give off energy, it just wouldn't be visible energy, and that's what we need to make our camera work. We need visible light, right? So thallium degrades the crystal enough that the electrons in the crystal, when they're calming down, they give off light. That's the simplest way to remember. I think that's as far as you would need to know for the test, but just know that that's what thallium is for, okay? Now, another thing that people get wrong a lot, and even on one of the practice tests that Shauna was showing me, again, and I'll be honest with you, I didn't like all the questions on that practice test. I thought there were some that were way too complicated and also just off in left field. So I'm going to work on making that better. But I will say that remember that your crystal is a crystal that covers all of the photomultiplier tubes. It's one crystal, so it's like a sheet. Think of more like your source you use to do floods in the morning, right? The crystal is like that. It's a sheet that goes across the entire gamma camera. It's one crystal. It's not a crystal on each photomultiplier tube. It's one crystal. It's about 1/4 to 1/2 inch thick, and it covers the entire gamma camera head. So remember that, because that could be something that trips you up. Also, remember that it's hygroscopic. What that means is that it can absorb water from the air, so they're sealed. They have to be sealed so that they don't absorb water from the air. If they do absorb water, that messes with their ability to function correctly. And then also remember they're heat and cold sensitive. This could easily be a question on a test. Same with the heat and cold sensitive. If you had a test question that said, why do you have to maintain temperature in your gamma camera room or something, you would know it's the crystals are very heat and cold sensitive. Remember what hygroscopic means. Remember that sodium iodide is thallium activated and what the thallium does. All those can easily be questions. This is the chart I had to explain that scintillation and what happens as visible light. Again, I don't think you're going to be asked about these bands, understanding the valence band, the different bands. But just remember, in a crystal, there's these energy states, and it isn't the electron moving to a different place. It's just, think of just electrons get excited when they're hit by a gamma ray. And so they quantify these different bands as different excitation levels. And so again, all the thallium does is it makes it so that when that crystal gets struck, the excitation of those electrons only go to kind of a moderate energy level. And then when they calm down, they give off the visible light, okay? If that wasn't there, again, it would go up to this, what we call the conduction band, and it would calm down and give off energy, but in a different form, okay? So that's all we're saying there, is that just think about how excited an electron gets. You need thallium to make it not quite get so excited. Proportionality is super important throughout the process, right? We talked about that. About when a photon strikes the crystal, it gives off a certain amount of light, and it's dependent upon the energy of the photon. So tech at 140 gives off something different than thallium or than I-131, right? Because they're different energy levels, so different amount of light comes off. So photomultiplier tube, this is where we convert light to electric pulse. This is a chart of one. Remember that we have a cathode and an anode. We have what's called a photocathode. And so the photocathode is at the beginning, and that's what the electron strikes. The anode is at the end, and that's going to eventually kind of connect to our electronic circuit. Remember what these are called in the middle that amplifies our signal, okay? People got that wrong a lot. What are these circuits called? They're called diodes. And remember what's happening is there's a photon coming off from the cathode, right? It gets strikes it's like an aluminum of basically like an alloy. They can be different ones. It's a photosensitive alloy. So think of it as a photosensitive metal. When it gets struck by the visible light coming off the crystal, it kicks off an electron, and then there's a voltage across here because we have a cathode and an anode, just like an X-ray. And so it's pulled across that voltage. It's going to strike the first diode. Every electron that strikes a diode, it will kick off around four, sometimes more electrons. Those continue in a process of exponential growth as they each strike and produce more and more until we get to our anode and we have a signal big enough that it can be read. And it's proportion again. So you're going to have proportion across this whole process, okay? So remember, that's the purpose of that diode, is that it's going to multiply those electrons and it's going to increase that signal to where it's a readable pulse. And all this is written in here, so you can look at that as well, right? I'll let you look at this later since we don't, just for time's sake, but there's an animation. All right. So photomultiplier tube arrangement, you can have circular, hexagonal, or square, and they're going to basically be arranged behind the crystal in rows. That's all I want to say on this particular one. Yeah, I think I said most of it, that essentially you're going to have a pulse that comes out the other end, an electronic pulse, right? This is where we first get into the term photopeak. So you need to understand what photopeak means. And all its meaning is that electronic pulse. When we look on our camera, we looked on a spectrometer, we just see that pulse that happens. Just understand that's just an energy pulse. And it's going to be measured according to that peak is where the peak is located, how much is what isotope, or excuse me, not isotope. Let me say the right thing. What nuclide we're looking at. Let's see. Let's talk about positioning logic for a minute. So remember I mentioned that gamma camera is a crystal, right? And it's one crystal. So when you get a strike in a certain place, it's going to create an event that's going to come off in that spot as light. If you've ever shined light through anything that's like a crystal or glass or anything, that light can be, you might shine on one spot, but it kind of lights up the whole crystal, right? And so what's happening in your gamma camera is when an event strikes and the crystal lights up, it's going to have the most intensity of light where that event occurred, but there's going to be diminishing light as it spreads out. And so what positioning logic does is it divides your whole face of your camera into X and Y coordinates, right? And so each of those X, Y coordinates, just like when you did graphing in math, has an X and a Y value. And so wherever the photon actually struck on the crystal, the photomultiplier tube that's behind that is going to record the intensity of that event that it saw from the light coming off the crystal. And the rest of the photomultiplier tubes are also going to notice that event as it perpetrated through the crystal, again, getting dimmer as it goes away. Okay, and so all those crystals are calculating and saying, well, I saw this much light, I saw this much light, I saw the most light. And so they can coordinate and say where that event actually happened and then place it in XY coordinates. So when your photomultiplier tube sees that event, not only is it changing and intensifying the signal so that you can have a photo peak coming out the other end, but it's also maintaining where it happened. And that's how it does it. If it was only one photomultiplier tube and it saw an event, there'd really be no way for it to tell exactly where it happened other than to say, well, it happened in front of me somewhere. But as it coordinates with all the other photomultiplier tubes, that's how you get your X and Y positioning, okay? And then a Z, so we have the X, Y, and then the Z is the intensity, right? Because it records who saw it the most intensity. So that's what that does. So that's that's the way the positioning logic works in your gamma cameras on that coordinate system. So again, here we got kind of following through, you've got the crystal, you've got the photomultiplier tube. The next thing we're going to hit is a preamplifier, amplifier, and then the pulse height analyzer, which is where you can actually start to see and look at that pulse that we've been trying to essentially create this whole time. Okay, so just remember that the preamp is hooked right up to the back of the tube. That could be a question, right? If they say, where's the preamp located? It's located right on the back of the photomultiplier tube. It's close. And the reason it's close is because the signal coming out of that photomultiplier tube isn't that strong. It's just a pretty weak signal. So that preamp is just to boost it right at that moment to get it up to where it can start to be used electronically. And that sends it to then the amplifier, which is located in the camera, but further away from the location of right behind the photomultiplier tube. That amplifier will increase that output by about 8,000 times. Again, still keeping it proportionate. It maintains the X, Y, and Z. And it also will do some shaping of the signal. Okay, it'll make the signal a little more uniform of a signal, so it shapes it a little bit. And by the way, that's called corrections. When you hear energy correction, there was a test question on one of Shauna's tests that was about energy correction. That's what it's talking about, is the amplifier shaping that a little bit. I haven't hit on that very hard. I think that's a little deeper than what you might be asked. In fact, I went and looked, after I saw that question, I went and looked in your textbook, and there's like a tiny paragraph on it that's like about 4 sentences long. So it's one of those things where I have to choose what to include and what not, because Waterstrom tells you everything. So hopefully that doesn't get anybody. But if you're wondering, that's what that is that shaping the signal. Okay, so then we get into the pulse height analyzer, and that's where we can actually see our pulse height. Remember that in the pulse height analyzer, you're going to have a lower level discriminator and an upper level discriminator. This is where you set your window. So if you've looked at any of your gamma cameras, and if you haven't at this point, please go look. Please ask your tech, say, I want to look at the pulse height analyzer. It should be a screen that you pull up on your camera and you can see it while you've got a patient under there. Okay. So you set your lower limit and your upper limit to a window. Generally, it's about a 20% window. So if you had your 140 keV, that would represent where it's located or its center. And then you'd have a window for slightly higher energies and slightly lower energies. And that's basically the pulse height analyzer is what looks at this and says what is able to analyze what type of energy you're looking at, and then discriminate a little bit to settle that in on what energy you're trying to look at. Okay, and cut off things like sometimes you get what's called a Compton edge right here, where you get some Compton scatter that's kind of right next to the photo peak, and that window can kind of cut that out. Okay, so this is part of energy resolution, right? Is can we determine and have this peak be right at 140? And this is where I kind of just explained, here's all the things that can happen. When I mentioned earlier, and I was trying to tell you what energy resolution was, this is the slide I was thinking of. There's lots of things that can happen, right? When photon goes straight into a crystal and we get a nice event, then we should expect to see that event happening right at the photo peak. But we're going to have some Compton stuff. We might have some scatter off a patient, some lead off of a septa, getting a little bit of characteristic X-rays. There's a bunch of other things that do happen in a gamma camera despite our best efforts to block all of that out. And that's why this photo peak has some width to it, is because it's going to see some other energy levels. Think of it this way. That peak isn't your KeV isn't up here. This is just the number of pulses, how much of it it's seeing. So when it goes up really high, say I'm seeing a lot of this, the energy range is down here. So this one you're looking at right here is cesium, which has a 662 keV gamma. So that 662, it's seeing a lot of 662, seeing a little bit of like say 650 and a little bit of like 670. And then you have a few other things, and these are the other things being explained down here, a few other things that are happening in this energy range. So if you were looking at cesium and you were trying to image it, which we never do, but just for example, you would set your window, you'd set your middle right at 662, and you'd maybe do 10% above and 10% below, and then the camera would disregard everything else. Okay, so that's our energy resolution. Now, and this I already kind of mentioned this too, so I'll separate. This is when we talk about full width half mask. That's what you're measuring. Energy resolution, or excuse me, full width half max is just a way to measure the energy resolution to see if it's within an acceptable limit. So you have a pulse height here, right? There's your pulse height coming in. And this one is text, so it's seeing the main most counts at 140. And then we're getting some other stuff in here. And the question is I mentioned before, if that peak is super narrow, that means we're seeing 140 and only it's doing a really good job at only seeing 140. So that means we don't have a lot of scatter, we don't have all this other stuff going on. It's able to resolve that resolution and resolve it to a very small, narrow peak. So that's what you want in energy resolution. You want that to be very narrow. When it starts to get really wide, that means, well, wait, why are we seeing all these other energies? I only want to see 140, but I'm seeing all kinds of stuff. So what's wrong with my camera if this thing is so very, very wide? That's what you need to understand about energy resolution. And all full width half maxes is measure the size of that spread. Okay, so measuring the size of that spread. And the way that it's done, and I don't think you're going to have to do one of these, although Shauna's test did have you do one of these. But it's really not that difficult if you just kind of think of it in the basics. But you have your full width, okay, at half of the maximum. So the maximum number of photons you're getting here is somewhere in the neighborhood of events of 1,000. So if I'm getting about 1,000 at the 140 range, what I do is I say, okay, I'm getting 1,000, so let's go to half. So that's the half max part. Go to half max, and then I'm going to measure that full width at that half max. That's all that means, full width half max. So it's the full width at half of the height of the pulse. Okay, and so what they did is they saw it on this chart. They said, well, it was 132.5 is where this was hit, and then the whole measurement goes to 147.5. That's a difference of 15 keV. Okay, so then all they did is they took that 15 keV, okay, 15 keV, and then it's divided by the energy of the photon. Well, what photon are we looking at? We're looking at tech. So divided by 140. So 15 divided by 140. And then anytime we do ratios, right, to get a good number that's not decimal, we times it by 100. And so when they did that down here, it came up with 10.7%. So that's a percentage. So I wrote down here, good values for tech is 8 to 12%. So if we did this on your camera and it showed up like this, your camera is getting good resolution. It's within understandable resolution parameters. If we brought this up and it was like 20%, we'd be like, something's wrong with your camera. Something's not working right because it's not resolving that energy into exactly what you want to see. Okay, that's energy resolution. My feeling and what I've taught in the past is that understanding what full width half max measures, like how it measures what it's doing. In other words, you're taking that peak and it's at half the peak, and understanding that you don't want a wide spread and that your energy resolution is a measurement of how narrow can I be, and narrow is better and wider is worse. That's what I think you need to understand. I think if you go into your test with that understanding, you're going to be able to answer questions that come up with this. Again, can I 100% say that they won't make you solve one of these? I can't say that 100% because they don't tell us what's on the test. However, in all my years so far that I've had lots of students pass, I have not taught them that they had to be able to figure a full width half max equation out. So take that for a grain of salt, but definitely understand the principle going on here. Okay. Now, I'm going to show you something else, and I don't want it to be confusing because there's another place that we use full width half max, and it's not energy resolution, it's spatial resolution. So right here in the middle of my slides, I cut out really quick, since we're already talking about full width half max, and tell you what spatial resolution is and how they measure that with full width half max. Okay, so when we think of spatial resolution, what we mean is that, can my camera represent an event that happened, sternum in my body, be represented in the right place on the camera, right? That's spatial resolution. And we talked about how our spatial resolution isn't perfect because we have angled photons, but can it represent it in the spot that it's supposed to when it goes through all of the camera equipment and gets to that pixel on my screen? Okay. So the way this is done, and then you'll see how full width half max makes a little more sense. And I referenced this in Waterstrom, but there's a bar phantom that's hung above your gamma camera, and it's radioactive. It's one rod. It's like a rod bar, and it's hung a certain distance above the face of your camera. And what that means is that it's going to be giving off most of its radiation is going to come straight down, and you should have a spread of radiation going out. And so the question is, can your camera resolve where that's located in time, or not in time, in space, right? And so you should expect that if right in the middle, that's where it's located, that's where your most of your counts are going to be, but you're probably going to end up with some counts as it spreads across the face of your gamma camera, okay? That's what this curve represents. So this would be distance from zero, from the middle of your gamma camera where that bar is located, to the right and to the left on your head. And then this is the count rate. So you'll end up with a pulse looking just like a, similar. It's not an electronic pulse, it's a pulse saying this is where I see counts, okay? And so you should expect that right where your bar is, you're going to see the most counts, and then working out to the edge of your head, you're going to see less counts. What you want your camera to do is be able to mostly see the counts that are right in the middle, which is where they should be, right? Because that represents where your bar actually is. So you want to be able to see where it actually is, okay? And so it's the same principle. We say, okay, where do I have the highest counts? That's at zero, where my bar is. I'm going to go half max, and I'm going to measure the width, the full width, half max, okay? And they measure it the same way, and they do the calculation, and it's measuring the spread of resolution. Now, again, I don't want a lot of counts way out on my camera head. I want all those counts to be narrow, right where that phantom bar is, right? And so that you also measure spatial resolution with half max, and that's what it's doing. Again, I didn't even give you an equation here because that's not what they're going to be after. But if they want you to understand, what spatial resolution is and how we use full width half max to resolve that. Again, what do I want? I want narrow. I want a narrow spatial resolution, not a wide one. Okay. Okay. That gets us to our image display. Here's where on an image display I have the coordinates right again. So it's gonna as it goes through that whole entire process, it's gonna kick it up on our image display. It's gonna save that as ones and zeros. Every time a count hits, it gives each coordinate more value and more value, and that's how we form a picture, right? And the matrix, your matrix size can change based on the parameter that you set. And so this is a good review of matrix, right? Common matrices are like 64 by 64, 128, 256. So the thing just that you should remember here is that this breakup is not pixels on the screen. Matrices are not pixels on the screen. And it's confusing because we think of this as 64 by 64. We usually think of a screen in pixels. It's dividing, think of your camera head. It's dividing your camera head up into those things and then assigning addresses for each of those boxes that it's going to then count whatever is in that box and represent it on your image, okay? So obviously, when you have a 64 by 64, you're going to have a less resolution of an image. When you get to 256 by 256, you can see how many picture elements you have. You're going to have a lot better representation of an image, okay? And this is where I showed you how you could figure out the pixel size that is on your matrix. So you know actually what each part of it, how big you're measuring, right? And so on this one, I said if you had a 40 centimeter field of view, which is pretty common, and you divided that up into 128 by 128 matrix, so you'd have 400 millimeters. This is in centimeters, but I changed it to millimeter because we're going to end up with millimeters. So 400, you just do 400, divide that by 128, which is the pixels sizes, or the matrix size, and you get 3.13. So that'd be 3.13 millimeters per pixel is what's represented on your camera head. Okay, so just remember that. Other thing to think about when you talk about matrix size, and I hope that as you've gone through the program, and as you've talked about some of the things like, let's use bone scans, for example. When we do a flow, right, you have to think about the fact that every time a photon strikes that portion of the crystal, it gets a little bit more intense, right? In the case of your matrix sizes, if you make that square bigger, then more photons represent one spot of imaging. And so if you're doing a flow happens quickly, right? You're doing a bone flow, it's going to happen fast. So you need to have your camera be able to measure things quickly. And if your matrix size is really, really tiny, it's likely to miss those, because if you have a bigger matrix, more portion of your crystal is dedicated to giving you that part of the pixel on your screen. So that's why when we do like a bone flow, we usually do like a 64 matrix, because we need to be able to catch multiple events and represent them in one spot so we can get an image of the flow. But then when we change to doing our statics, we're doing like 128s or 256, depending on what your department does. Because at that point, you're just sitting them under the camera. You have time for each of those tiny pixels to gather enough counts to produce brightness or an image on your screen. Okay. Hopefully that makes sense. Just understand matrix is just an overlay, and it represents what portions of the crystal are going to be represented in on the screen. Okay. All right. So talked about frame mode or matrix mode, which is the acquisition where you have the XY coordinates and everything just gathers on the screen as it's happening. List mode is the acquisition mode where it's digitized and assigned an address so that it can be used later. Most PET scans are done in list mode. It gathers the data and then it reassigns on construction. When you do a SPECT, you're likely gathering in list mode as well so that it can take the list of addresses and reconstruct. You have to do that on things like when you gate for a heart, that's going to be gathered in list mode. It's going to gather each portion of the gate, and then you're going to tell it, well, I want to look at systolic, I want to look at diastolic, and that's going to gather it together from that list. Okay. SPECT. I think what I main points to hit here, getting close to an hour now. Understand there can be step and shoot, there can be continuous motion. What else? You can have body contours on your camera. Body contour is going to go into a contoured orbit around the body. You can have circular orbits. I think that's mostly that. You can look at that in a little more detail. The general operation, I'm guessing most of you have a pretty good grip on the general operation of how a SPECT works in terms of it rotating and things like that, because you've been doing it now for a while. So I'm not going to get super detailed here. Remember the difference between filtered back projection and iterative reconstruction. Remember that filtered back projection is where we project things across the matrix at multiple different angles until it forms an image. And iterative reconstruction is a mathematical process where the computer mathematically guesses and then it refers back to the image to look and see if it's correct, and then goes and corrects as it looks at each projection. So it looks at projections, it just doesn't put the projection across the matrix. It references the projections as it makes mathematical calculations. And I'll let you look through some of this. Any questions about filter back projection or how it works? I'm inclined to skip this because I know I hit it hard when we looked at it, but I don't want to leave anybody confused either on how it works. Puts things in sinograms. This video is great. You can actually I just found this online by Googling filter back projection video, and this came right up. So that's a good one to watch if you need to. I guess we can just push play on it real quick. So it's recorded right here. Part one is that acquisition. So you're going to see projections going across the matrix and forming a sinogram. A sinogram is formed for each slice, and your slices in your gamma camera are represented by each row of that matrix. So each row of matrix as it goes around is going to have its own sinogram of projection data. And then it's going to reconstruct the object, throws it across the matrix, does it in multiple places. And then remember, the filtered part of this is that it then filters anything that's outside of the main image. And we're going to talk about a couple of filters that are generally used too. And then there's the iterative reconstruction again. I don't think you need to know specifically how this math works. Just know that it's a mathematical, then guesses and refers back. That's why they call it iterative, because it's multiple iterations that the computer does as it guesses where things should be. There's some advantages and disadvantages of the two types. Iterative, one thing nice about iterative, if you have anything in there that's like some kind of error, like a ring artifact or streaking, that's not included because it doesn't need to throw everything across the matrix. It just goes back and refers to the image and then fills in, counts where it does that mathematical guess. So you don't need a lot of the filtering either, which is nice. It can make really good images, but you need a really good computer. Most computers nowadays handle it just fine, but it takes a lot more memory and can be a slower process. And just remember, filter back projection is simple, easy, goes fast. But again, we can end up with artifacts that come through because it accepts everything across the matrix, any energy level that it sees, and then has to try to filter it out. Okay, filters. Remember these. These are probably going to be questions. You need to understand what a high pass filter is and what a low pass filter is. Just by the name of it, I want you to think, if I say high pass filter, just on bare reading that, what am I saying? Saying high, the high frequencies get to pass through the filter. Okay, high pass filter. So on a high pass filter, what that means is low frequencies get blocked out and high ones are let through. Okay, what's a low pass filter? It's the low pass. It lets the low frequencies pass. Here's the part we need to memorize is that low frequencies are responsible for more of a smooth effect in your image, but not sharp and really resolute. Whereas high energies are more sharp, okay? They're sharp and less blurry. So you have to think whatever I'm letting through is going to show up more in my image. So if high frequencies show me sharp images, then a high pass filter will sharpen up my image. Low pass filter, if I'm letting lows through, it's going to smooth out my image a little bit. Give me 1 second. I have my car in the shop and I have to hurry and make sure this isn't the. I'm going to do a quick 5 minutes. I have to give this lady that's fixing my car a warranty number real quick. So take 5. Hang on a second. We'll get right back into this. Sorry. I wouldn't normally take this call, but I have to. Sorry about that. Hopefully some of you got a drink break. All right, so yeah, we're talking about those high pass and low pass filters. Those are kind of your two main types of filters and how they work. And then the most common type of high pass filter is a ramp filter. And there's a picture of it here. So remember that the high pass filters let the highs through. So these higher frequencies up here get through and it erases like the blurring. So this sharpens up the image. A ramp filter is what's commonly like generally applied to a lot of your images to sharpen them up. It's a ramp filter that's generally used in filter back projection as well. So remember ramp filter. And then the other two that I'll put on here is the Hanning filter and Butterworth. These are the other two very common filters. I do believe there's other types of filters out there. I think these three will get through your test just fine. Both the Hanning and the Butterworth are low pass filters, so they let the low signals through, and that's what you see as you look at the graph here. On the Hanning filter, you've got kind of a smooth transition from lows to then cutting out the highs. And you can change the frequency. Most time a filter will give you a bar to use, and you can slide it back and forth to kind of have more effect or less effect. The Hanning filter cuts pretty steep and kind of levels off in a smooth way. The Butterworth filter is also a low one, but it kind of keeps the lows longer and then cuts off really fast down to the highs. So you can see the differences on the images here. You start out with an unfiltered image, and then you look at how much of that filter is applied, and it gets smoother and smoother. And so that's the effect they have. So I would know those three filters going in. I would understand what a high pass filter and low pass filter does, what that means. And then I would understand what ramp filter is a high pass filter, and then the Hanning and Butterworth as low pass filters. But I think generally understanding what a low pass and high pass is, however the question is worded, it will help you get through those questions on the test. And then just remember QC on a camera, uniformity daily, spatial resolution is weekly. That's with your bar phantom. CORs, again, I've seen some places that do it weekly and some places that do it on more of like a monthly basis. And then peaking. Peaking is not one that you need to think about too much. Peaking is what peaking does is it's your camera checks for the photo peak to see if the photo peak is aligned where it's supposed to be. Oftentimes that's done automatically within your camera as part of like your floods and things like that. So I've given like more details here. Thing I would remember about floods is they shouldn't be more than 5%. When you get those numbers at the end, you shouldn't see things greater than 5% on your normal daily floods. Remember the difference between intrinsic and extrinsic. When we do an intrinsic test on our quality test on our cameras, that means that we've got floods on when we do it, or floods off when we do an extrinsic. The floods, or sorry, I'm saying totally the wrong thing. The collimators is what I was trying to say. Collimators on and off. So remember those. You know what a flood should look like by now, I'm sure of it. Spatial resolution. So these are kind of the numbers on spatial resolution. I don't think they're going to ask you there's no specific number to know on spatial resolution. You just need to know that you should be able to see on a bar phantom the separation of all the different levels of thickness of lead. And then on a for SPECT spatial resolution, you'll have a JSAC phantom, which looks like this, and you should be able to see all of the spheres. CORs, I don't think they're going to give you a specific number, but just understanding what a COR does when it should be done. I think that's it. Any questions on gamma camera? I got more wordy than I wanted to. I'm sorry, you guys. It's hard not to. It's a lot of stuff. You guys need a break? do we keep going, or do you have questions?
No, I'm good.
Okay. All right. Okay, I'm gonna do equipment next, and we'll kind of see our time value. I might have to be done close to 6, so we may not get to PET and CT. But again, I will have all my old lectures are available on my YouTube, and then I'll have slides. I'll make sure slides are posted on Canvas so you can go through slides as well. And again, like if you have a burning question that you came to this with, I'm fine with you asking those now as well. I don't want you to leave with the question still just because I was yakking looking at my slides. So if there's any of those, maybe we should even just do those now and then we'll buzz through the rest of this.
There was only one question that I had that was like showing up in the bolus books, and it's totally unrelated to what we were talking about. But we were, or a lot of the questions were like about plasma and hematocrit and plasmacrit and that kind of stuff. I don't remember talking about that in class. Is that something that we went over that I missed?
Well, I would assume that they were talking about values for doing like a certain type of scan. I don't know that that's necessarily like physics and instrumentation because a hematocrit is a measurement of blood. I'm trying to think what that would have been applied to.
I don't have my bolus book in front of me, and I, like I said, it's totally unrelated to what we were talking to,
Yeah,
but
yeah, no, that's a good question. It could have been.
it was like calculating like plasmacrit or something like that. And I was like, I don't think we talked about that in
I
class. I don't know if I should focus a lot on it.
I probably wouldn't. The only thing I could think of that the two things that are ringing in my head, and again, they're just out of whatever's coming in, is when you do the pledgets could have been something where you're looking at some sort of concentration with although that would be I don't know. That is really
Okay. I just probably won't
I'm
waste
gonna
a lot
say I
of
don't know. I don't want to just lead you on some random tirade of mine, but you can pass that one by Shauna too. That I don't know. That's
Okay.
again that's the difficulty with like trying to find nuke med questions out there and then even the book itself. Some of them are just I don't know.
Right. Yeah. I'll just look in the book if anything, but I didn't figure
Yeah,
it was something I was going to worry about too much.
yeah, I wouldn't stress too much about it. Sorry, I hate giving that answer, but
No, that's all right. Like I said, we didn't talk about it in class, so I'm like, is it really that important? I don't think
yeah,
so.
yeah, probably not. Could you get a question on something like that? It's possible. I'm gonna guess most people don't. But
Okay. Perfect. Thanks.
anything else, guys? Any other questions? And if not, I'll kind of try to get through this last section. Um, this is where we'll look at like our meters and things like that and review that real quick. Okay, let me share that and then we'll let you loose. Okay, can you see the slides?
Yes.
Okay. All right. I'm going to skip some of these kind of initial ones and just kind of get to where we're talking about the actual instrumentation and what we're using. Um, some of these are the same slides as terms of like efficiency and things like that and sensitivity. A lot of this applies to anything you're using to detect radiation. So I'm going to skip through all that and get right to our gas field detector. So remember that a gas field detector has argon gas in it. The thing you need to remember here is there's an anode and a cathode, so a voltage is applied across from the anode to cathode. And when gamma rays strike or any type of photon strikes, you have ion pairs that are created. That gas gets separated electrons come off, and so you have electrons and those ion pairs, and the electrons being negative get attracted to the anode, and ion pairs get attracted to the cathode being positive, and that creates a voltage across the system, right? It creates amperage, and it measures that amperage. So that's the general idea of how a gas detector works. And remember that the greater the radiation coming in, the more ion pairs will be created, but it's going to depend on our voltage level. So that's the thing we need to get to kind of discern or discriminate between the types of gas-filled chambers that we have. So remember, along the bottom of this chart here, you've got voltage. So as we increase voltage going this way, and this is the number of ion pairs that are collected or made or make it to the cathode or anode, okay? So when we first start this process out, if our voltage is very low, then all that's going to happen is those ion pairs are going to be created. There's going to be separation, but there's not enough voltage to pull them to the cathode and anode. So they'll separate momentarily and then come back together. And that's what we call a recombination phase. So there's really nothing that happens in the recombination phase, but it's important to talk about it because to start to get this idea that we get a separation, but voltage is all dependent on what we end up doing with this meter on how it's attracted to the cathode and anode, okay? So in the saturation range, that's one of our more important ranges. What's happening here is that you get a proportion of how many photon events come in creates a certain amount of ion pairs that give you a measurement on your meter, okay? So if you're using a gas-filled chamber and you're getting a measurement of some kind, whether that's counting counts or whether that's counting MR per hour or anything like that, that is in the saturation range, okay? Anytime you're getting some kind of meter, you're measuring the amounts, you're measuring how many ion pairs have been created. So if you have something where you're just getting a beep and it goes away, that's going to be your GM meters. And anything in the saturation range is going to be your where ionization is happening, and you have a proportionality, okay? So that's the thing to remember is that proportionality. So more photons equals more current. The more photons you have, the more current will show up, and that's where your meter will go up. When we get up into the GM range, what's happening up here is that the argon gas is being hit, that separation is happening, and then you get what's called a cascade effect where everything in the tube goes off and it has to be reset before it can then come back on. So if you've got a real Geiger meter counter that's a gas-filled chamber, all you're going to get out of that is the beep, 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 beep. And each of those beeps is the whole entire process of an avalanche happening and then the system resetting. Okay, it's not going to give you like a measured thing. So I have that process written out right here on this slide, which is where the cascade or the avalanche effect. And I think generally you need to understand, they may ask you about an avalanche or a cascade, and you need to be able to understand what's happening in this process. So this is a really good graphic. This shows the walls of the tube are going to be your negative, and the anode, the positive, is a wire in the middle, okay? So what's happening is when you have that radiation come in and it's striking the argon gas, it's going to separate, and you're going to get an attraction of the electrons down to the anode wire, and you're going to get an attraction to the walls of the ion pairs, okay? And what's happening here is that when you have your voltage turned up high enough, that separation of those pairs is going to go to the cathode and the anode with more force and more power. So if your voltage is turned up to that GM range, what's happening is as this travels toward the anode, it's then striking other gas particles and creating more ion pairs and more ion pairs. And it's this avalanche of that happening, right? It's a cascade that happens, and each one of those is doing that along the way. That's going to happen until pretty much all the argon gas in the entire system has been separated and you've created those ion pairs. The other thing that is in here is we talked about the sorry. The oh man, sorry, I'm losing my train of thought. Oh, that's what I want to talk about is what does it mean to quench? Okay, so that avalanche has to be stopped before it can respond to um, another event. The time it takes for that whole event to happen and then for things to reset, that's your dead time. So if you hear the word dead time, that's anytime an event has to occur and then be reset. There's a small amount of time. Now, on most of your like meters, you're talking about milliseconds. These things happen in millisecond time ranges. Okay. What else do we want to put on here? I'm trying to think if there's anything else I mentioned on this one. Oh, I didn't mention that that some of this, when it strikes the walls of the tube, will create ultraviolet light, and ultraviolet light is also emitting part of that cascade. I highly doubt we're going to have to get that deep into it in terms of a test. But the idea of understanding what an avalanche is, and then understanding that there'll be dead time as the system resets. Um, one thing one thing you will need to know is what a quenching gas is. So they add an organic type of gas, usually it's methane, and that type of gas doesn't it doesn't ionize, but instead it breaks down into smaller molecules and absorbs some of the ultraviolet light, and it kind of slows down the process after the argon has been all split apart, and that's called a quenching gas or quenching the system. So understand how an avalanche occurs, and understand that it occurs because you have really strong voltage making things travel a really hard path. And then understand that there's going to be another type of gas, usually a natural gas, something like methane, that's going to quench that. And so if they talk about quenching your meter, it's kind of that gas that kind of slows everything down and lets everything reset. I'm trying to think of anything else. Oh, you can, that's what I was going to say. On your meter, usually on your meter, there's a sticker, and I think it mentions this, but if not, you can find your manuals, but it will tell you what your dead time is on the type of meter you have. And it's usually like nanoseconds. It's really short, like 40 nanoseconds or something like that. So really, really short on those dead times, but that's how it works. I think more likely questions that you're going to have is what type of meter you're using for what. Okay. And so when we say ionization chamber, we're talking about anything in that range where it doesn't have the Geiger-Müller effect. So the Geiger-Müller is where everything shoots off when the voltage is really high, and then it has to reset. The ionization chamber is where you're measuring. So just remember that ionization chamber, anytime you're measuring anything for proportionality or to get an actual measurement. So anytime you're going to send your patient out the door, let's say you do an I-131 treatment, and you've got to measure, what their MR per hour. Anytime you're getting an MR per hour, anytime you're getting a number of counts, anything like that, when it comes to gas field detectors, it's going to be an ionization chamber. Geiger-Müller, or a GM tube, is going to be where we get that full beep. You're just trying to detect radiation. So Geiger-Müller counters are usually very sensitive, and you're going to use them in low level of activity. So this would be like you're trying to detect low amounts of radiation in some area. And all you're looking for is that one beep. So it's very sensitive, and it does not have proportionality, which means it can't give you a measurement. That's a GM tube, that's Geiger-Müller. Ionization is going to give you a rate. It's not as sensitive because we're actually measuring radiation with it, like a radioactive patient or things like that. There's not going to be dead time in an ionization chamber. It's just going to constantly give you a measurement, whereas a Geiger-Müller is just going to be on and off. That's it. This gets confusing with the types of meters that are out there. And remember that your meter that you work with at work, the meter that shows the numbers and has the dial on it, that thing can attach to an ionization chamber, and that can attach to a GM Geiger-Müller, like a pancake probe, which is a Geiger-Müller. So because of that, you have to think of just what your head is, and especially when you're working, at work and knowing what you're dealing with there. So most of the time, uh, you're going to be dealing with one of those two, and a lot of them are interchangeable. Okay. So, but again, in terms of tests, just understand what type of gas filled chamber does what thing. Again, the low sensitivity, the high sensitivity. If they say something like, I need to measure and find what's my most sensitive measuring device to get low level radiation or something like that, you're going to do Geiger Mueller. If they say, I need to measure my patient before they leave, what type of gas filled detector am I going to use? You're going to say ionization chamber. Okay. Um, Quality control. Again, they're usually calibrated annually or any repair. That's something to remember. Remember, there's a sticker on the side that has the calibration dates. And also a sticker on the side also comes with your cesium button, so you can measure what it should be. It shows what the measurement should be on the side of your meter. All of that should be contained on the sticker on the side of your meter. So I could see that being a question like, here's the side of the meter, what does this information give you, or what is it saying? When is it calibrated next? Things like anything like that would all be on that sticker. Should be within 20%. I guarantee that's a question. Survey meter should be within 20% of whatever's on the sticker. Dose calibrator. What do we want to say about this? Just realize again, it's a gas filled chamber. Again, it's not a GM. It's not in the GM range because otherwise we just get an on or off. It's ionization range or saturation range because we actually put our doses in there and we can measure how much they are. Remember that all it's measuring is the amount of ion pairs created. And so on a dose calibrator, the electronics have a factor for each button that you push for the different things that you measure in your department. There's a factor applied to that, but all of them are just seeing the amount of radiation. So a factor is applied to all those. And when you do your dose calibrator QC, your daily QC on your dose calibrator, that is what you are checking. As you put your standard doses in of cesium or cobalt, and essentially what you're doing is you're checking each channel to see that it's remained the same over time. I think I have those listed too on this. Yeah. So here's all of your dose calibrator QC. This is definitely going to need to know this. Hopefully most of you just went through all of this because you did your working on your quality control manual, your QC manual. 10% is a number to remember. And notice that 10% triggers a repair on accuracy. You'll notice 10% on geometry. 10% is like a number all throughout. I don't know why I don't have it listed. Constancy should be the same thing, 10%. I did have someone contact me and say that I think it was Mettler book. I didn't verify this, but the Mettler book had 5. Every other source I look at has 10%. And so I would go with 10%, not 5%. I haven't checked that on Mettler, but 10% is the number you want. Do you guys want me to go over what these are? I think the thing you should remember here is when it's done. So accuracy is done annually, and remember the 10% limit. Constancy is going to be daily, and it's going to be done on each of those channels that applies a factor for each nuclide that you use or each isotope that you use. Linearity is measuring over time, is it able to track with radioactive decay. And then that's performed quarterly. And then geometry is anytime you have a vial size change. So if you go from using a syringe to using vials, anything that time your vial size changes, geometry has to be performed to measure things for the type of vial you're using because it changes where the radiation is located. And so that geometry has to be within 10%. And then usually that's done when your dose calibrator is set up as well. So any other questions on that? Any dying questions? You probably just went through all that. Again, I like this chart because it's simple. Well counter, just remember that a well counter works exactly like your camera. It's a scintillation device. The thing I would remember about a well camera is, again, it has really good sensitivity, and the reason being is that you literally have a hole drilled into your crystal, and so you're able to set your whatever you're measuring right down inside the crystal, which means it's gathering almost 360 degrees, so that's as sensitive as we can get. And again, we're not using any kind of collimators or anything, right? Because you're just trying to get an amount when you're putting the well counter. And so extremely sensitive because of that high sensitivity. Your maximum amount of activity that you can put in there is about 1 microcurie. So it's not very much because it's so sensitive. When you get above 1 microcurie, it'll still give you a measurement. It's just not likely to be super accurate. So remember that. But in terms of functionality, you look at this and it's exactly like what's on your gamma camera. Crystal, photomultiplier tube, preamp right at the back of it. Okay. Thyroid probe, same thing. I go over these quickly because functionality wise, they work the same. We don't use it for imaging. This even does have collimators, but it's just a single hole collimator because again, we're not trying to image out of it. We're just trying to get counts, measure thyroids. The rest of functionality for thyroid probe, I leave to your imaging classes where you learn what to do and how to measure a thyroid and where to place things like that, all part of that. In terms of just the functionality of it, it's really just like your camera. So we leave it pretty simple. Let's see, do I want to go any further? And we'll get into the stats. I'm not going to put you guys through statistics. So, all right. What do you guys want to do? I need to be done by about 6 o'clock. If you want, I can go into and look at least briefly through the pet stuff for the next 10 minutes. Or if you have some more questions, we can do that. Don't all speak at once.
I'm good with everything.
You're good? Okay. If there's not any questions, I'll give you the next 10 minutes on the pet. We can at least get through some of it. And I'll pretty much skip most of the CT stuff. I really think for CT, the main thing that you need to understand with CT is the general basics of what KV does and what MA does, which I think most of you have from that X-ray background. And then really we use it for being able to locate anatomy, right? And really helpful in our PET scans, especially oncology. And then the other thing is just being able to do attenuation correction. You need to understand attenuation correction and what it does and what it's providing for us, basically. All right, let me get this up. Try to make this brief. Okay, we already talked about positron emission. Again, it's beta plus, right? Remember that it travels a short distance and then has an annihilation reaction with an electron. Remember 511, there is no PET nuclide that measured at any other energy than 511, which makes it easy for the camera. We just tell the camera to look for 511 and that's it, right? Understand that in PET, the different nuclides have a what they call a max range and a mean range, and each PET nuclide has its own resolution. What that means is that annihilation, or excuse me, when the positron is kicked out of the nucleus, it travels a short distance and then annihilates, which means because you image the annihilation, it's slightly away from where the actual anatomy or where the nuclide is located in the anatomy. So there's a little bit of resolution that happens there. And so a longer travel is less resolution and a shorter travel is better resolution. Okay. So we have to remember that when it comes to PET. And so these are some of the different nuclides, and you'll notice their travel ranges. FDG is really good. Rubidium that's used in cardiac is not so great, but there's other great things about it. But you can see the differences, right? So PET nuclides have a resolution, and that's what they're talking about. Production of nuclides are done. Are usually done in linear accelerators or cyclotrons. We talked a little bit about that in our review. The crystals, let's talk about the crystals. So the crystals used on PET are different than the sodium iodide crystals that we use in gamma. They've got to be a more dense crystal. They've got to be thicker because they got to be able to stop that 511 keV photon. Okay. The other thing that they need to be do is measure light quickly and then dissipate because of the way that they work. So we like fast decay time. We like high density and high energy. So this shows the types of crystals compared to sodium iodide. And you'll notice like their densities, decay times. Decay times are super important with PET. PET is really based on timing more than it's based on seeing events, like a gamma camera sees the event and just records it. PET is based on those two 511s striking at approximately the same time, approximately 180 degrees apart. So the ability for crystal to be able to reset and get back to ready to accept another event quick is really important. So great crystals are ones that are really fast, that are dense enough to stop it. And then you'll notice that none of these are hygroscopic, and none of them have the water problem, which is nice compared to sodium iodide. The crystals design, we'll go to this picture, it's easier. The crystals are designed as blocks. So you have a photomultiplier tube behind blocks of crystals. The crystals are separated. These separations are about 3 to 4 millimeters, and that is where you get your resolution on a PET scanner. So you have the resolution of the nuclide itself, but then you also have the resolution of the camera, which can't get greater, or can't get, I should say greater. It can't become smaller than the size of these crystals. Each one of these crystals records a single event that's then portrayed onto the photomultiplier tubes. So you can't get smaller than that. These are what they actually look like. These are 3 millimeter crystals. This is how we get our 3 millimeters resolution on a PET scanner. Now remember, when you go over to SPECT, the SPECT world, it's about a 12 millimeter resolution. When you look at a static on a gamma camera, you get about 3 or 4 millimeters of resolution too. You just can't reproduce a SPECT 3D image and have it be 3 millimeters. It'll be about 12. So that's why PET is far superior, because all of the images are reconstruction images at 3 millimeters. And again, we can do whatever we want with our reconstruction, right? We can do axial, coronal, sagittal, and that's all going to be 3 millimeter images. Design of PETs are all in rings, 40 or more consecutive rings. That's what makes up the field of view in a PET scanner. It's also what each of these can make up the slices for a PET scanner. You might hear the term electronic collimation. We don't have, the normal bores and holes like we do in our gamma camera. And it's because we are electronically collimating. And what that means is that as those photons travel apart in opposite directions and strike the camera at different sides of the camera at approximately the same time, there is a timing window, and it's nanoseconds. And anything that strikes within that timing window is considered a true event. And if it happens on the opposite side of the camera, then it will give us what's called a line of response. Okay. And so we get these lines of response that go across the camera. There's also something called time of flight, where not only does it create a line of response, but it measures the difference between when these two struck, and it places it within about a 9 centimeter distance in the middle, which improves resolution again. These lines of response are what form, before I do that, True count is when that happens within the timing window. You can also get random counts that appear to be the same, but they happen from different events. And then you can also get scatter as well. What they'll usually do is they'll gather, your computer will gather a delayed window. So past 12 nanoseconds, anything that happens earlier than 12 nanoseconds, we consider it a true account. Anything after 12 nanoseconds, they know that those are random accounts, and it can take a map of anything that it was after 12 seconds and apply it to what it thought was true counts and cut out any excess random accounts. I don't know if you're going to need to get that detailed, but just understand that a true count is when it sees it on both sides of the detectors within the timing window, and random counts are pretty much everything else. Same reconstruction principles apply, but instead of one projection, your reconstruction is made up of those lines of response. So lines of response that are parallel to each other become your projection data. So it works very much the same when you're reconstructing the image. Just, again, all of those lines of response across the matrix. So that's what I've shown here. You have many lines of response. Again, there's the spect, how it's forming its image as it's casting across the matrix, and PET is casting the lines of response across the matrix and essentially forms an image in the same way. You can see a sinogram just like we went over before. You have filter back projection and iterative. Most PET scanners use iterative or a combination. If you hear about these other ones, MLEM, OSEM, RAMLA, most of those are an iterative type of reconstruction that uses some filter back projection, but mostly uses iterative reconstruction. I think there are some questions in your books on that. I don't think those will be on your test. I wouldn't spend an inordinate amount of time about the different types of reconstructions. Time of flight I kind of mentioned earlier, which is it can kind of look at the times that it hit each side of the camera and get a measurement within about 9 centimeters, and then only use 9 centimeter lines of responses to form to do the reconstruction, which means it cuts out a lot of noise or anything that's outside of that 9 centimeters. That's another picture of the time of flight. I'm not going to go over 2D, 3D differences. You can look at that if you want. Every camera that you'll be dealing with is a 3D camera. 2D used to have septas. Just the thing I would have you understand on this picture is that when we say a camera's 3D, what it means is that even crystals on different rings that are adjacent on different sides of the camera can gather events that happened at the same time. It's not just each crystal is exactly apart from each other, but it can catch it in almost all directions. So this is one of the things that makes PET centers super sensitive and not need a septa, is because there's that electronic collimation. Again, and here where I mentioned PET being around 3-4 millimeters versus 12 millimeters on SPECT. CT, again, I'm not gonna hit a lot of this. I just don't think you're gonna be highly challenged on CT stuff. Just understand, again, KVP is your penetration. It's controlled by voltage, and so it's kind of the strength of your X-ray, whereas MA is the amount, and it's controlled by current, so it's the amount. Appropriate MA and KV are going to give you good images. So I will show you this really quick. Here we've got 80 kV with 200 MA, and we notice we have it's pretty modelly, and that's because this kV is pretty low, and so you're not getting enough penetration through the tissue. Over here you've got a really nice contrast and resolution using about 140 kVp and 200 MA, and so you get this nice looking image. Down here you notice both of them are low. You've got 80 kV and 30 MA, and so you're getting this ring artifact. That means some of the camera isn't even turning on or isn't even getting a response because it's not getting enough penetration through the body. There's not enough photons and there's not enough push to do anything. And then here you notice you're getting a high kV, so you're getting the push, but you're getting low MA. And so it gets a little modelly. Now, coincidentally, when we do some scans, like especially in cardiology, we go ahead and do this low MA. It's not a great diagnostic CT, but it works for attenuation correction because the resolution of the CT only needs to be as good as the resolution of the PET scan itself. Okay, so that's something to remember with attenuation correction. You can do a low dose CT and save your patient on the dose and still get the attenuation correction as long as the resolution is at least as good as your PET scan. So that's why we can use low dose. So in most of your oncology stuff, you won't use low dose because they want to see the anatomy as well. However, in cardiology, you're mostly only using it for attenuation correction, and therefore you can use a lower dose. I don't think you're going to get a lot of this X-ray stuff. I would generally understand what a Hounsfield unit is. They measure water, and the attenuation level that water gives on your scanner is set at 0, and then everything that's more dense than water gets a value of up to somewhere around bone, which is 1,000, 3,000, and then down to air, which is like -1,000. So that's Hounsfield units and how they measure attenuation. And don't worry about most of this stuff. So this is where I'll say that combined PET CT imaging, which is what you'll probably be questioned on, is understanding again what attenuation correction is. And so the biggest thing to understand is that attenuation just means that parts of an anatomy are more dense than others, and so they attenuate the X-ray photons more, and that's how we get a CT image or an X-ray image. Is that areas that are darker on the image, more has gotten through, and areas that are lighter, less has gotten through. So usually with bone is pretty white looking, and a lung is more dark or black, right? And so when we have that understanding, then when we're doing a PET scan, we can attenuate, the body parts are different. Everybody has different body habituses, and our images are dependent upon photons being able to reach the camera. And so thicker body parts can block those photons at different strengths, and it can make it look like there's less radiation in an area on our image than others. And so if we know how much attenuation is in each area of the body by looking at a CT scan, we can take that CT scan and apply it to either our gamma scan or our PET scan. And then what the camera does is it will say, okay, anywhere where I see a anatomy that's dense based upon the attenuation in the CT, then I will increase the counts in that area proportionally. And so it makes up for things like a large breast tissue or something like that that can block some of our imaging. So I would just know that that's what attenuation correction is. You're not going to have to try to calculate anything or do anything. You need to understand what attenuation is and how it uses CT as its way to be able to measure the attenuation of the body parts and then give back counts where they're needed. And that's what this graphic right here represents. It represents this area looked like it was low in counts. We applied the CT on top of it, and it came and smoothed everything out. Okay, I think that's about it. Like I said, I'll make sure a lot of this is I'll make sure all of these slides are on the Canvas, and I'll have that available. And again, if you want to do deep dives and all this, I'll make sure all of my sorry, I'm trying to end my share here so I can see. There we go. I'll make sure all of my slides are available and videos on my YouTube channel, and you can study through as much as you want. But I think that's all I have for you today. Any other questions? Hopefully this was somewhat helpful to at least kind of review some of the basics. It was quick, so sorry about that. Anything else? I've either put you all to sleep or there's no questions. Okay, well, I'm gonna end it. All I'll say is just good luck. You guys are gonna rock this. Everybody, you guys are all gonna pass. I know this is a hard time and you're studying like crazy and you feel like you have no time for anything and you're all scared to death, but you've made it through the end of the program and go get those tests taken. Take them sooner than later. Even if you don't feel like you're prepared, you're more prepared than you think you are. So good luck and it was nice knowing all you guys. I'll let you go.
Thank you.
You're welcome.
Thank
Thank
you.
you.
Welcome.
Thank you.